Okay. So half-lives are a way to describe the rate at which a radioactive compound will naturally decay, and decays exponentially at a rate that we call a half-life. So a half-life, one half-life is the amount of time it takes for half of a radioactive sample to decay. I can look at an atom and say this is a radioactive atom, but I cannot say it's going to decay tomorrow. That's how unstable it is. Or it's going to decay in 5 seconds, or it's going to decay in 100 years. Instead, I can say for this sample of 100 atoms, statistically speaking, I can expect half of them to have decayed in this certain amount of time. And a half-life for each radioactive species is different for each. And so you can't just say without knowing which one you're talking about. But for example, carbon-14, I think, has something like a 5,000, 5,200 year half-life kind of a thing. I've got strontium 90 in my lecture notes. It's got a half-life of about 30 years. So that gives you an idea. So, you know, about 5,000 years, about 30 years. And a lot of the really heavy nucleuses that we make by fusion in the lab, like californium, for instance, those things are going to have a half-life on the order of seconds or minutes, and maybe even fractions of a second. So it depends for which one you're looking at. But if we look at this on a scale, what we find is that if we start up here at time equals 0 with 100% of my sample, all of my sample, then after one half-life, so time and half-lives, after one half-life, I'll have 50% of my sample remaining, because half of it will have decayed. Does that make sense? You guys with me so far on half-lives? Okay, so then from this time going to 2 half-lives, then I will lose, I get half again of my sample. So instead of 50%, I'll be at 25%. 2 half-lives. So 1 half-life to get here and lose half my sample. Second half, I go here and I lose half of my sample from the last data point. At 3 half-lives, then, how much of my sample will remain? %12.5%, or half of 25. Excellent. What about 4 half-lives? 6.25. Excellent. So hopefully you guys can see, and hang on a second, this is not going to be a pretty line, but it's going to be a line. We call this exponential decay because it never really reaches 0. I mean, it can get to the point where the background radiation is on par with the radiation that you're getting from your sample, but you're just always getting half there, half there, half there. Also, what I want you to note is your fraction here. At this point, you have half of your original sample remaining. At this point, you have 1/2 times 1/2 of your original sample remaining, or 1/4. At this point, you have 1/2 times 1/2 times 1/2, right? And at this point, you have 4 of those halves. Everybody agree with that? Feel comfortable with that? Another way we can express this is to say this is 1/2 raised to the first power, because there's only one of them. This is 1/2 squared. This is 1/2 cubed. This is 1/2 raised to the fourth. Everybody feel good about that? Okay, so what I want you to notice then is that the number of half-lives that have elapsed is the power that you raise your 1/2 to when you're determining how much of your sample is remaining. So if 3 half-lives are passed, then I raise the number 1/2 to the third, and that tells me what fraction, what percentage of the original amount remains. Everybody make that connection? So we could turn this into a mathematical formula and say, well, the amount which is remaining divided by the original amount that I had, this is the fraction, right? The fraction that remains, like 0.5 or 0.25 or 0.125. This is going to equal 1/2 raised to the number of half-lives which have elapsed. Everybody follow me there? Maybe if we apply it, it'll be a little bit clearer. But that's exactly what this is saying, that if 50% remains, or if 1/2 remains, that's 1/2 raised to the number of half-lives, which is 1. And if 4 half-lives have occurred, then the fraction that remains is going to be 1/2 raised to the fourth, which is going to be 0.0625. That's the fraction. Okay, so let's say, for example, we've got a sample of strontium-90. Has a half-life, we call this T1/2, that means half-life, of 28.8 years. So if I have a 5-gram sample that I'm storing it, then the question is, how much will be left after 85 years? Did an experiment with strontium-90 when I was 20. I was done with it, disposed of it. By the time I die, how much is still around? Say I live a really long time, for instance. Now, if I look at this information with regards to the equation that I just gave you, we know that the original amount is 5 grams, right? We want to know the amount remaining, so that's going to be X. We need 1/2 here. We need to find out how many half-lives have passed. How do we determine how many half-lives have passed? Do we know how long one half-life is? (28.8 years. Let me write this equation slightly differently. 1 half-life equals 28.8 years for this problem, okay? and how much time has passed. "85 years." Can I use dimensional analysis to determine how many half-lives have passed? Yes. I need to cancel out years and I need to be left with half-lives. So what do I do? "28.8 years on the bottom. And 1 half-life on the top. So I'll cancel out years and that will give me an answer in units of half-lives. So let's say here, I've got 85 divided by 28.8. So I've got 2.951 half-lives have passed. Okay, I think I have all the pieces I need to plug this into my original equation. So my amount remaining, that's what I'm asking for. How much is left? That's x. Divided by my original amount, which was, what's my original amount? 5 grams. Good. That's going to be equal to 1/2 raised to the number of half-lives, which I just calculated to be 2.951. And now I solve for x, which is just a little bit easier said than done because everybody's calculator now is a little bit different. But if I'm raising something that's not 10 to something that's not like 1, 2, or 3, this gets tricky. On this calculator, I'm going to use the x to the y button. You might have an x to the y button or a y to the x button, or you might have a little caret that you might have to use instead. And depending on which yours is and what model, it's going to change what order they want you to do it in. But in this case, I'm going to say 1/2 is my x, so 0.5 is x. And then I'm going to hit that button and it's going to say, all right, what's your y? That's a little caret. So if you don't have the x to the y button, look for the caret and then you can just put in 0.5 caret and then you can put in the other number directly, 2.951. So 1/2 raised to the 2.951 gives me a value of 0.1293. This is the fraction that remains, right? Just like here, 1/2 squared told me that 25% remained. 1/2 to the 2.951 tells me that 12.93% of my original amount remains. And since I know that I originally had 5 grams, all I have to do is say, okay, well then 0.1293, which is the fraction that remains, multiplied by my original 5 grams, and multiplying that by 5, I will discover that 0.647 grams remains. Of strontium 90. Did everybody follow what I did there? Or if not, can you articulate where it was that you lost me? Robin's with me. Excellent. Oh, well, excellent. Well, let's go into the in-class activity sheet and try this. Okay. So here we go. Oops. Gold 198 has a half-life of approximately 2.67 days. So 1 half-life equals 2.67 days. All right. 14.5 nanogram sample is used. So my original amount is for leukemia treatment. How much will remain after 8 days? What will be left after 8 days? Now this is important because often when you go in for radiation treatment and then you're treated with something like gold, then you need to know how long it's going to be before it's safe for other people to be around you, because you are radioactive. For as long as that thing inside you is radioactive, you are radioactive too. And you don't want to harm others. So we want to know how much is left so we can tell whether it's going to be safe to be around. So walk me through, how are you guys going to do this one? Okay, dimensional analysis starting with what? So 2.67 days is one half-life. Oh, we need to find out the number of half-lives that have passed. You're right. And 1 is 2.67 days. So 1 half-life, 2.67 days. Get rid of days. We're going to say 8 days have passed. That'll tell us the number of half-lives that have passed. So 8 divided by 2.67. So we've got 2.996 half-lives. Excellent. Now this is about equal to 3. So if we want to estimate, we can actually round that off to 3. Let's do both and compare to see how close our answer is. Okay, now what do we do next? Excellent. 1/2 raised to the third, or 1/2 raised to the 2.996. Okay. 0.5 raised to the third gives us a fraction of 0.125 remaining. So 1/2 raised to the third equals 0.125. And then what do we do? And then multiply by the 14 nanograms. Excellent. So the fraction that remains multiplied by 14.5 nanograms equals 1.81 nanograms remains. Now let's see if we use 2.996. If we use that instead of 3, if we didn't round. That still gives us 0.125. Still gives us, that would give us 1.82 nanograms, but it's close enough, we'd pretty much get the same answer. Excellent. Okay, I did intend for these problems to round to whole even numbers to make it easier on you. But let's see how to do it both ways, because it's nice to be able to check your work here. These next two are basically identical problems. So let's do the second one with you guys. We'll play around with it. So half-life is 8.10 days. And now I'm asking how long it's going to take for a 50-gram sample to decay to 6.25 grams. So from 50 grams to 6.25 grams, If we look at our original equation, essentially we're going to say the amount that remains divided by the original amount is going to equal 1/2 raised to the number of half-lives. And that's what we don't know. We don't know how long it was. So now we have to solve for x. You guys following me here? If I know how many half-lives and I know how long each half-life is, I can determine how long that was. But this is the piece I don't know. I don't know the number of half-lives. I do know what remains. I do know what I started with. So I need to solve for x. There is an easy way to do this, to estimate the right answer. And then there is a more complicated way to do it to get the exact right answer. Here's how we're going to estimate the right answer. We're going to take our 50-gram sample and we're going to divide it by 2 until we get to 6.25 grams, right? So after 1 half-life, I've got 25 grams remaining, right? Everybody believe me on that? After 2 half-lives, 12.5 grams remain. And then after 3 half-lives, 6.25 grams remain. So that is 3 half-lives. Did everybody follow what I just did there? Yeah, that wasn't so bad. 25 grams, 12.5 grams, 6.25 grams. Okay, that was 3 half-lives. Now, if it didn't come out perfectly, let's say I said 6 grams, then you might say, oh, it's probably a little bit more than 3 half-lives. You can kind of estimate there a little bit, right? Because 4 half-lives would take you all the way to 3.125. So you can do a little bit of estimation. Here it came out perfectly to 3 half-lives. And if each half-life is 8.1 days, then we had a total of 24.3 days transpire. Everybody see how I got that answer? Okay, that wasn't nearly so bad as it seemed at first blush, was that? When you first read the question, how do I do that? But this isn't nearly so bad. You guys can do this. You can do this estimation. And in this case, it wasn't even an estimation. It turned out perfectly. Now here's the other way, just a teeny bit more complicated, but it has to do with the properties of logs. I put this down here. These are properties of logs that we saw when we did chapter 10, although we didn't talk about them explicitly. This is just how we got from, say, the Henderson-Hasselbalch equation back to the K of A equation in your buffers. But here's the useful one for half-lives. If I take the log of anything which is raised to something else, then it'll pull that other thing out in front. So log of x to the y equals y times log of x. I could use that property and say, let's see, where was I? There I was. If I take the log of both sides, then I can say the log of 6.25 divided by 50 equals x times the log of 1/2. And now I just have now I can solve for x by just dividing the log of 6.25 over 50 by the log of 1/2. So if I take 6.25 divided by 50, the log of that, and I divide that by the log of 0.5, I get 3. X is 3. So that tells me that it was 3 half-lives, because that x is my number of half-lives. And then again, I multiply by the number of days in 1 half-life. and I can find the total number of days, how long it took to decay from 50 to 6.25 grams. Again, just a little bit more complicated, but much more precise if you don't have exact numbers. Yeah. I'm sure that you guys learned all of these things at one point in time in your algebra class. I'm also pretty sure that you have never had to review them until you got to chapter 10, is my guess. I could be wrong. So yeah, at one point in time. So this might be a nice little refresher. Again, anytime you use a log is by definition what we call base 10. So the log of 10 is actually, because this is 10 to the 1, essentially, when I say log of 10. That's why the log of 10 is 1. Anyways, okay. I will let you guys do the thallium one on your own because it's the same as the iodine one. It would be good practice. These last two questions have to do with just dimensional analysis. We're looking at dosage and exposure, radiation exposure, using some units that you might not have seen before, but I think that given your knowledge of the metric system, you guys should be able to do these. I'm just gonna, because we've only got a couple minutes left and I know you guys want a little bit more review. Let's look at, for instance, something like this. If you've got 3 milliliters dose and your activity is 9.5 millicuries in 1 milliliter, well, we can just use dimensional analysis. That little m is milli. The CI is curies, which is a radiation dose. Your milliliters cancel and you'll get the dose in millicuries that was received by the patient. Okay, so nothing fancy for these, it's just using dimensional analysis with some of these units you might not have seen before. Okay, let's stop this.